2 years ago, Joseph Penninger gave one of the really remarkable talks at TED, and it's a pleasure to have him back. Joseph.
Okay. So it's a pleasure to be here in this glorious place. Actually, I was on stage doing flamenco dancing, but I won't spare you this today. It's true. I was in the second row, yes. Yeah. And it's true. I can still do it a little bit. I'm a little reluctant today to speak to you, actually. And the reason is my sister-in-law died last week, and I saw her dying. So she had breast cancer 4 years. She survived it 4 years. She had bone marrow transplants. She got chemotherapy for 4 years. She was bleeding out of her eyes. Her teeth fall out. It was just awful. So last week, finally, her kidneys failed, and more or less she died in my hands. And so anyway, I'm sorry. At the end, life ate her, cancer ate her life. But I wanted to tell you about some things we're doing in my laboratory in Toronto, and I'm now moving to Vienna too, because there's better cakes there. And as you have heard, we are really in the age of exploration, of genetic exploration. What people did 500 years ago is explore the world with ships, find new ways, made maps of the world. And what we want to do now is make a map of the genetic world. And Sidney Brenner once said, it's nice to have all genes, but it means nothing unless we actually know what these genes are doing. And so this is what we're trying to do, to give names to these little valleys and little rivers of our genetic world. I'm too fast here. So one thing we have been working on for the last 4 years is actually a gene we call OPG ligand, and by pure luck we actually hit on it. And the reason was because we wanted to find the molecules which determine how much bone we have. So there are lots of diseases which are associated with bone loss. 200 million women have osteoporosis. Arthritis leads to bone loss, to crippling. When we're old, we're losing our teeth. So there are lots of diseases. And so we tried to find the genes which control these little guys here, bone-eating cells, and how we could manipulate this. And so what we're doing is actually we are genetic engineers. We do gene targeting, so we can punch out every single gene in the genome of a mouse and then create an animal and then ask the question, what happens to these animals when the certain gene is missing to get to the biologic function of it. And this is what happened. Oops, I really can't figure this out, jeez. So this is a normal mouse, and I can't figure this out. So anyway, so on the top one is a normal mouse, and when we mutate the gene OPG ligand, you see the mice are tiny, and the reason why they're tiny is the following: the bones are completely solid. So there's no bone marrow anymore. Every single bone in these little guys is completely solid, and after lots of work, what we actually found is the osteoporosis gene. And after 20 years of search, we basically found the osteoporosis gene, and there's now a molecule which blocks it, the biologics, and it kind of works like insulin for diabetics. And I'm not joking, every time when there's bone loss, we put this in, and it completely shuts down bone loss. And we're using this now to block osteoporosis. We had shown that you can block arthritis. We can actually block tooth loss, so the teeth cannot fall out anymore of these guys. And last year, this protein flew to space with NASA because people and astronauts are losing lots of bone when they're in space. And so it turns out it really works well to shut down bone loss in space flight. And who knows, in the future our kids will use this stuff when they fly to Mars. One thing which is really close to my heart is cancer metastasis. So my sister-in-law actually had this really vicious metastasis into the bone. I'm told 1 million people actually get bone cancer metastasis a year. It really hurts. The clinicians tell me it's called breakthrough pain, so you cannot even treat it with morphine anymore. So these people are just in severe pain. And I can tell you, my sister-in-law, when she came to us visiting in the morning, she was just screaming because of the cancer. So actually, when we use this and shut down bone loss, we can actually control pain in bone metastasis, which probably won't prolong the life of people, but at least they have a decent life and can go on with their lives. Another gene we have been working on is something we fall over. It's called the dream gene, and I think we started working on it because it had a really neat name, and so we might as well work on the dream gene. And for 2 years we tried to figure out what the dream gene was doing until we found it controls pain. So this is an early picture of pain control. You see even the elephant takes it. So this is actually pure alcohol. So this was the major pain controlling medicine in 2 centuries ago. And I show you the dream mouse. So this is my student in my lab, Mary, and she mutated the dream gene, and you can see this beautiful little guy here. So that's a dream knockout mouse, and we also sell it in pet stores if you want it, so to finance our research in Canada. So, and Mary actually looked for 2 years for what is dream doing. We couldn't find anything until we realized what dream was doing, it controlled pain. So it turns out when we switch off the dream gene, the mice have much less acute pain, they have much less belly pain, they have much less arthritic pain, they have much inflammatory pain. And we also set up a system for neuropathic pain, so for back pain. And sure enough, our guys have much less back pain. And the US Congress declared this decade actually the decade of pain research. And I have been told 50 million Americans have chronic back pain. And so what we are trying to do is basically to switch off the dream gene to control pain information, and this is how it's working. So if you cut yourself, so your pain gets in the spinal cord and in your brain, and you have to respond to it. So it's a vital sense. So if you do not know this is cold or hot, you're in big trouble. And so dream actually allows this pain signal to go through, and you respond to it. However, when we switch off the dream gene, the spinal cord neurons are swimming in our own opioids, and it completely switches off pain. And so the idea we're having in the future is actually, if we have no dream, we have no pain. And so that's one thing we're working on. So probably people will here talk about bioinformatics and how we can push the borders of medicine with computer technology. Well, what I actually think where the real edges, the real borders are, is imaging technologies to marry genetics, things we are doing, so we can change genes in animals as we like it now, and actually then marry it with imaging technologies. For example, in pain research, what we really would like to do is, so the mouse feel pain, and we develop a helmet over the head of the mouse, and then we map in 3D every single neuron which is firing now. We found a new gene in mice which controls our clock, and when we switch it off, basically the mice do not know when they sleep anymore or when they should be waking. And so that's what we want to image, which neurons respond to light, and of course this takes us all the way to how people get depression when they don't have light, why they commit suicide and things like this. So one disease we are really interested in, it's really for personal reasons. A person very close to me had a stroke 7 years ago, And since this time basically cannot move and talk anymore because of cardiovascular diseases. And of course it's the major killer on our planet. So we got into it originally because we worked with the virus. It's called the Coxsackie B3 virus. It tends to infect little kids. So these kids get this very severe heart disease, the myocarditis. There's nothing you can do. You just have to put them into intensive care and hope that they're surviving it. So this little kid actually didn't survive it. It died later. And so we started working on Coxsackie virus, finding out how our white blood cells controlling the infection. And as an aside story, I was once invited to a bioterrorism conference in the US because I guess they wanted to know if we can engineer a Coxsackie virus which would kill and give heart disease to certain ethnic groups, which I found really intriguing. And anyway, I declined to go there. But serious, this is what people are working on. Once I was actually approached by the US military to help them with our bone work if one of the soldiers is shot, that the bones are regenerating much faster, so they're shot and 2 days later they're running again. But for heart disease, the risk factors we know, high blood pressure, smoking, obesity, and there are lots of genetic factors which control heart disease. So we all know somebody smokes a lot, they're healthy until 90, the next guy smokes a lot and they get a heart attack when they're 40. And so we wanted to know the genes which control heart function to basically define molecules, give names to valleys and mountains which control how our hearts are functioning. And to do this, we went back to flies. So this is actually a fly embryo. And we did this because many people do now gene arrays, and we actually gave up on gene arrays again because we found so many genes and we had really no use for them. It was just too many to deal with. So we went back to genetic screens. So we use a marker which is called, oops, my goodness, this is too fast for me. Oops. So we use a marker which is called Eve. And this little cells here, you see, this is actually the cells which will become the heart of the fly. And so we looked for genes which control heart development in the fly. And so we came across one gene which was angiotensin converting enzyme number 2, which was very curious because in humans it controls blood pressure, and in humans there was only one found. So we thought the flies have 2 enzymes like this, so we sure enough cloned the human gene, and this is what we did. And to make the story very short, of 3 years of work, turns out angiotensin converting enzyme number 2, ACE2, is a major factor which controls heart function. And when we mutate it, this guy is actually going to heart failure. And our mice look actually like humans with coronary artery disease. And it's very exciting. And I heard recently in a meeting that actually people looking now at genetic polymorphism, so differences in genes in the general population, and turns out that this gene is actually a major polymorphism for heart failure phenotypes in humans. So this takes us straight from mice to humans. And in most heart disease, if somebody has hypertension, if they have a valve defect, if somebody has a heart attack, so what the heart is doing is it fights against it and it starts to make more muscle, something called cardiac hypertrophy, so the heart becomes larger because it has to pump better. And if you push the system, so if you squeeze the system, what you get is, so you get really expanded heart, dilated cardiomyopathies, and heart failure. And so we looked for genes which control heart failure and heart size, and these are 2 genes we found. One is very interesting, P10, it's a tumor suppressor. It's a molecule which controls breast cancer and ovarian cancer. And another one is PI3 kinase gamma, which controls how our white blood cells are moving. And for example, when we mutate the P10 gene, we get mice which have huge hearts. So we can actually play around in animals, and we can create animals which have normal size, but their hearts are twice as large. We have animals where the hearts are tiny. And then we found other genes which actually control heart function. And at the short of it, so we can actually now create genetically animals, mice which have huge hearts which are failing, mice which have huge hearts but work much, much better, mice which look like a normal mouse but the heart is half the size of normal. So we basically can completely uncouple how big the heart is and how the hearts are functioning with these genes we found in our fly screens and in the screens in the animals. And why are we doing this? Can we actually use this to protect from heart failure? And so we did this, so we injected something really nasty in this mice called isoproterenol. And on the top you can see this little red streak, so these mice get very sick. After 1 week they have heart failure. However, when we mutate this gene P110 gamma, what is happening is nothing. They're completely healthy. They do not go into heart failure. And one of our competitors did now the same for heart attacks. Turns out if you switch off this gene, you can really maintain heart function in heart attack. And as I said, we went from the little guys, from the flies, to the mice. But I don't want to leave you with the impression it's only genetics which control how our hearts are working and how we can control this. So it turns out the major risk factor nowadays for cardiovascular disease is actually C-reactive protein, a protein which turns up when there's inflammation. So people believe now inflammation, viral infection, bacterial infections might be a major trigger for heart diseases. And many people, at least 50% of people who get heart disease in the 40s or 50s, have no risk factor for obesity or high cholesterol, so there must be other explanations for this. And so we looked for systems where we can actually model this, where we can model heart inflammation and then see what would happen to hearts and how we can interfere with this. And so a postdoc in my lab actually came up with this really neat new system. So he takes pieces of the heart, feeds them to special cells, which are called DC dendritic cells. So these are not senators from Washington, D.C. These are our dendritic cells in our body. So he takes little pieces from the heart, feeds them to the cells. And people had tried this, but with his little magic hands, he actually changed the system. And 1 week later, when we put back 50,000 of the cells, we put them back in a completely normal mouse, the heart is completely inflamed. Severe autoimmune disease, like diabetes, type 1 diabetes, like MS, like lupus. So we can actually do exactly the same with heart disease. And it's a really neat new system. And why I'm telling you this? Because we believe doing this, we came up with the unifying idea how autoimmunity develops diabetes. And what we need for this, and it always works in our hand, is you need an injury. So somebody's running a lot, so you hurt your knee, you have a genetic susceptibility, but this alone does nothing. It makes maybe somebody gets it faster or not so fast. There's one signal which is absolutely necessary for the disease to occur, and this is an infection. So in our hands, in terms of this heart disease model of autoimmunity, we can never induce the disease if there's not an external trigger of an infection. We even set a heart attack in mice, gave them infection, and what these guys got, severe inflammatory heart disease. So our life is really not just defined by the genes, but our genes define how we respond to the environment. And we actually believe there's no autoimmune disease if there's no infection happening at the same time. So why is this actually interesting? For other reasons. And the reasons are people try to do cancer vaccination. So how do you turn on your own, the ideal thing to vaccinate against cancer is you turn your own immune system on, so somebody has breast cancer. So you want our own white blood cells to attack the cancer cells, kill the cancer cells, and to trigger autoimmunity, and the cancer disappears. So people tried it, it really doesn't work well. And with our new little magic tricks, it actually works really well. And so the whole idea is what we want to do now is, and what you're doing now, is take cancer cells, feed them to our little cells we found, treat them the special way, and then give an infectious trigger, and what we're predicting is they're killing the cancer cells with their own immune system. And what's really neat about this, clinicians actually tell me when the people who have cancer and they get the flu, in some people, half of the cancers disappear. So the treatment of choice actually for bladder cancer is apparently a bacterial infection with BCG, a variant of tuberculosis bug. So I think by pure mistake, working on something else, we might have hit on the system where we can actually modulate vaccination against cancer. And how our system also works in this heart disease model is, so we feed this little heart proteins to the cells, give back to the normal mouse, the healthy mice. 1 week later, they have this massive disease, then they're actually healing again, and they go into heart failure later on. And then later on, a month or 2 months later, we came with an infection which is completely unrelated to the heart disease. Within 1 day, we have a relapse. And this is, of course, what people see with MS. Somebody has a flu, and boom, they go again and get sick again. So we actually predicting cancer vaccination might work. So that's the first time I actually predict this in public. Cancer vaccination might work, that we have an infection, feed them with breast cancer cells. So we kill the cancer cells. 3 months later, the cancer comes back. And then all we do is just trigger this infectious pathway again. And so we should turn on the system again. So this is our hope and wish. The reality, of course, is very different. So Bruce Chatwin, one of my favorite writers, he once said, he wrote this book and it's called What Am I Doing Here? And I think that's really the major question we face in our life. So what are we doing here? Because when I looked at my sister-in-law the last 4 years, so there's lots of hype, there's this really neat work people are doing, but the reality was there was just no new treatment out there. So the treatment is cutting and burning it with things people used 50 years ago. And so one thing I would really wish is so that people get together and actually take this and really try to develop things. And really for the sake of people, I think it takes a lot of courage to have new ideas. And my sister-in-law so she had 4 years this treatment, and every day she went to work. So she never missed a single day of work. In the morning she had chemotherapy. In the afternoon she went to work. So she had this unbelievable courage. And because she had this courage, I want to do something for her I've never done before, unrehearsed. So I hope I don't make a complete fool out of myself. And this is, and then I stop. And so thank you for listening.